Hopefully you get a chance to try these exercise 4.9 problems. And here's the first one. Notice this one looks a little funny because it's 1 to 0 instead of 0 to 1. So there actually are a couple different ways you could solve this problem. Let's do it both ways and kind of see how it works. So the first thing we're going to do is just keep everything the same. And I'm just going to find the antiderivative. What is the antiderivative going to be? It's going to be 1/4 x to the fourth. Notice this number has to increase by 1, and then you divide by your new numerator. Minus 3 times 1/3 x to the third, so that increased by 1, plus x, evaluated from 1 to 0. Okay, so this becomes, notice this right here is just the number 1, so I don't actually have to write anything out there because that ended up being really nice. Okay, now I just plug 0 into this. Always plug the top number in first. And we get 1/4 times 0 to the fourth minus 0 cubed plus 0 minus, and then I get 1/4 times 1 to the fourth minus 1 cubed plus 1. And then this looks like 0 minus, and then I've got 1/4 minus 1 plus 1, so minus 1/4. So it looks like negative 1/4 is the answer that I got. But there was another way we could have done the problem, and that is we could have switched it where the 0 was on the bottom, and we could have switched it to 0 to 1, and then it looks a little bit more like what you expect it to look like, or at least a math professor would expect it to look like. And what you would see is that this is now, but what happens is when I switch the order, I have to make it negative x cubed plus 3x squared minus 1 dx. So now when I have this, I could do the problem this way and end up with the exact same answer. I want to talk about one more thing, and that is what happens with the constants. So you all knew that when we did antiderivatives, we always had a constant show up. So for example, this one could have been 1/4 minus x cubed plus x. Well, we always had a plus c in here. What if we left the plus c in our problem? What would happen? Let's write it in red so that we can see it really well when we do our problem. So what if we had a plus c in our problem? Well, what would have happened is right here, we'd have had a plus c right there. And then we would have had a plus c right here in this part of our problem. Now notice what happens when we simplify. When you simplify, you would end up with 0 plus c over here. 0 plus c minus, and then this all again went to 1/4 plus c. But what you see is we have a plus c minus 1/4 minus c, and that this c and this c cancel each other out. So this c and this c cancel each other out. And so you actually don't have to write the plus c's on there, because every time you put a plus c in there, they would cancel each other out whenever you end up doing the subtraction. So you'd have one here and the negative of it right over here. Oops, it should have been minus. And the negative of it right over there. So so we don't need to include the plus c's when we do when we do our antiderivatives. It's just something we don't have to worry about. Okay, let's jump over to the second problem and see how it went. And the second problem was the integral from 0 to pi of sine of x. How is this going to work out? Well, this is the antiderivative of sine of x is cosine of x, except you have to have a negative sign. I know it's tempting to not put the negative sign, but that's because the derivative of cosine is negative sign. So to make it match, you have to have this. Okay. And that's from 0 to pi. And now we just plug those in. And so we get negative cosine of pi minus negative cosine of 0. And now if we look really closely, cosine of pi is -1, so we've got negative 1 minus negative cosine of 0 is +1. So this looks like it's 1 plus 1, and our answer is 2. So that one wasn't so bad, right? So you know, sometimes when you see these trig functions, you get a little intimidated, but it actually worked out pretty simple because we know what sine and cosine are. Okay, let's try the last one. And in the last one, we have to do a little bit of algebra first to make it all work out. So our last one is the integral from 1 to 3 of x squared plus 1. Now first let me write the wrong thing. The wrong thing to do is to write 1/3 x cubed plus x over 1/3 x cubed, because we know that division doesn't play nicely with derivatives. So why would it play nicely with antiderivatives? It doesn't work. And by the way, there's no quotient rule, but there are kind of ways of doing problems that have division in them. But this one is simple because this one we can actually get rid of the division by unsubtracting. So you can unsubtract. So to unsubtract, this makes our problem the integral from 1 to 3 of x squared over x squared plus 1 over x squared dx. And that means our problem is actually the integral from 1 to 3 of 1 plus 1 over x squared, and so that's x to the negative 2 dx. Now, this is a lot more complicated than this. This one is pretty simple. Now we're ready to take the antiderivative, and so the antiderivative of that problem is x. Let's see, what happens to the x to the negative 2? It's going to become x to the negative 1, and then we have 1 divided by negative 1. Negative 1 because if you add 1 to negative 2, you get a negative 1. It's tempting to go the wrong direction here, but that's actually what it is. And then we put our line, and we put 1 and 3 on it. Okay. Notice that this, I'm going to simplify it right here with my finger, and simplify it into just x minus x to the negative 1. When I put 3 in, I get 3 minus 1/3 minus 1 minus 1 over 1. This becomes 0, so it looks like 3 minus 1/3 is my answer, and that happens to be 8/3 is what we get. Okay. So we've kind of learned how to work these out. Hopefully these calculations are making a little bit of sense. Let me take just a moment though and talk about what the part 1 of the fundamental theorem of calculus is. We introduced part 2, and part 2 is the one that you use like 95% of the time, 99% of the time, and that is we take an integral by using an antiderivative. But there's another form, and the other form involves this funny equation. And this funny equation is what we call an accumulation function. And the way you should think of an accumulation function is this. We should think of it as you start at some a, and you have some function here, and then x is here. But don't think of x as one number. Think of x as a number that continues and keeps moving. So when x is small, you have this strip here. But then x increases a little bit, and you get some extra area, and then x increases a little bit more, and you get extra area. And so x is what happens as you sweep to the right. How much area do you have accumulated? And so this is often called an accumulation function. Well, the question is, what happens if you take a derivative of an accumulation function? And notice that this is taking a derivative of an integral. And the final answer, which I'm not going to spend too much time proving, and this is too bad because I really love this part of calculus, but the final answer is that the derivative of this integral just gives you your function x back. So this brings us to really the big idea of the fundamental theorem of calculus. So the fundamental theorem of calculus has one big idea. I put 2 i's. And the big idea is just this, and it's that we have derivatives on one side and integrals on the other side. And the big idea is that these two are really inverses of each other, or opposites of each other. And as I said in one of the previous videos, this is somewhat surprising because this derivative problem is just the problem of finding a tangent line to a curve. So I have some curve looks like this. This is the problem of finding a tangent line versus this is the problem of finding area. So they're inherently different problems, but it turns out that they are opposites of each other. So in other words, if I want to take a derivative, so suppose I have x cubed, if I want to take the derivative, I do 3x squared. If I want to do integrals, I have to go the opposite direction, and I do 1/4 x to the 4th. So we do the opposite action to do an integral as we do to do a derivative. They're inverses of each other. And so if you take an integral and then take a derivative, like in this one, if you take a derivative and then take an integral of it, you get the original function that has no derivatives left, right? In other words, if I take an integral, I can use an antiderivative to get my answer. Here, if I take an integral and take a derivative of it, I get my original function back. This is an antiderivative, what shows up in the middle here. Okay, so this is really the big idea. We had a student who's a quite popular student around here who always called it the uppy thingy and the downy thingy, and that was the way he talked about derivatives, because he thought of it as when you go one direction, you're taking derivatives, and when you go the other direction, you're taking integrals. And so he would say, oh, no, I need to do the uppy thingy, and I need to do the downy thingy. And although I don't recommend necessarily this language, I like the way he's thinking of it, and that is derivatives are going one direction, integrals are going the other direction. All right, so the good news for you all is there's only one section left in the book. I know there are two left in your notes. We're going to skip that last section. But there's one more section where we talk a little bit more about integrals and a little bit more about this fundamental theorem of calculus and do a little bit more practice. So if you're making sense, if you're caught up to this point, you're in really good shape. So I'll see you in the last video and once you go hit play.